Welcome to the Control Engineering webcast, Robotic Applications, What Robots Should and Shouldn't Be Doing, sponsored by Denso Robotics. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering and CFE Media and Technology. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RCEP at rcep.net. A certificate of completion will be issued to each participant. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RCEP. In this course, we will review related control engineering and plant engineering robotic research results and advice. Identify new robotic applications and the enabling robotic advances. Learn how to avoid the gee whiz effect when deciding if new robotic capabilities are right for your applications. And receive tips and tricks about robot and robotic system applications. To get the best results from the webcast platform, please make note of the following as you participate in today's event. If you're having technical problems, click on the question mark at the top right corner of the screen to bring up a list of system checks to make before escalating to an online technician. If you're experiencing issues with your slides or audio, please refresh your browser or click the Refresh Media button directly under the presenter's headshot. You can control the volume settings of this webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you need a technician, type a message into the Ask a Question box and someone will get to you as quickly as possible. Answers to your technical questions will be in the Answered Questions box on the left side of your screen. You can use the Ask a Question box on the left side of your screen to type questions for the speakers during the presentation for the Q&A session at the end. You may ask questions at any time during the presentation and we'll get to as many as time allows. Questions for today's presenters will be answered verbally during the Q&A session at the end of the webcast. To download the presentation slides, use the Event Resources area on the left side of your screen. To take the Learning Unit exam, use the Learning Unit Exam tab option at the top of your screen. The exam will open in a new browser window. You can complete the exam after the webcast, however, the link will break when the webcast signs off. The exam will be posted with the on-demand version of the webcast. The exam is for 1 RCEP ACEC Certified Professional Development Hour. This webcast is being recorded, including the Q&A session. We'll post the archive on the Control Engineering website in a few days and send you an email with a link to the archive once it's ready. This event is a live educational webcast presented March 12, 2020. The educational category is Technical, Health, and Safety. And now, a word from our sponsor. As one of the world's largest automotive parts manufacturers, Denso has been a leader and pioneer in manufacturing automation, including the design and manufacturing of industrial robot arms since the 1960s. Denso is also the world's largest user of small assembly robots, from 4-axis SCARA robots to the 5- and 6-axis articulated robots. More than 20,000 Denso small industrial robots are employed in the company's own manufacturing facilities, and more than 80,000 additional Denso small industrial robots are used by other companies worldwide. We welcome to the webcast today Evan Gonnerman, Controls Engineer at Concept Systems, who specializes in robotic automation integration. He graduated from Oregon State University in mechanical engineering and applies skills learned in this field to control complicated machinery. Exciting jobs included high-speed materials handling and assembly using synchronized robotic arms. Hiking, traveling, playing sports, and board games are among his interests. Ryan Wasman, Sales and Marketing Director at Concept Systems, began as a robotics engineer more than 15 years ago for a robotics integrator with automotive focus. He worked for an aerospace industry, manufacturer, and engineering, robotics, machine vision, 3D scanning, and robotic standardization. He served as Division Automation Manager at a metal fabrication company. I'm Mark Hosky, Control Engineering Editor and Content Manager since 1984. First, we're going to look at research results about robotic applications. The Control Engineering and Plant Engineering, CFE Media and Technology, Robotics Research Report was developed to better understand the trends and buying practices related to industrial robotics. A 2019 survey of 118 Control Engineering and Plant Engineering subscribers asked questions about use of robots and related hardware, software, peripherals, robotic safety, training, installation, integration, maintenance, trends, and purchasing habits. Margin of error was plus or minus 9%. From a list provided in the survey, we asked respondents which robotic applications are in use. The diversity of robotics applications is wide. 47% of respondents said they have material handling and conveying applications. 34% said they have pick-and-place applications. Other leading applications include machine vision using visible light, light assembly, packaging, palletizing, and welding. Still in double digits, others filling out the top 15 applications are stationary machine tending, medium assembly, identification and sorting, mobile robots parts delivery, quality control, 3D machine vision, CNC operations, and heavy assembly applications. 3 types of machine vision are listed on this slide and the next slide. Machine vision can be involved in quality control, palletizing, pick-and-place, assembly, and in other robotic applications. Continuing these robotic applications, this slide lists 14 others: infrared machine vision, electronics assembly, 3D additive manufacturing, grinding, filling, machine tending, mobile robots, painting, warehousing mobile robots, autonomous forklift mobile robots for order fulfillment, mobile autonomous drone for industrial mapping, mobile autonomous drone for industrial inventory, bottling, and buffering. Some of the largest areas for growth are mobile robot and mobile industrial applications. 7 mobile robot applications include part delivery, machine tending, warehousing, and autonomous forklifts. There's a lot more information in the report, but I wanted to show the enormous diversity of robotic applications before Evan and Ryan continue. Ryan, please go ahead.
Thank you, Mark. Really great data. Really excited to talk about some of the robotic applications that are out there. But before we get into that, there's definitely a lot of reasons why we should and shouldn't use robotics. And before we get into talking about why we shouldn't and why we should use robotics, Evan and I are going to talk about some new robotic applications. While all of these aren't traditional industrial applications, the research and knowledge gained from these systems can be applied to industrial applications. For example, search and rescue robots listed on our slide, they don't have an industrial application at the moment, but the research and development that is going into a legged robot or a snake robot will allow autonomous guidance, machine vision, and kinematics to be developed that will have a significant impact on industrial robots over the next 5 to 15 years. Again, with many of these new robotic applications, while we can't directly apply them to industrial manufacturing, we are already starting to see applications using some form of the developments that were born from these applications. Household robotics, such as vacuuming and mowing lawns, has led to some pretty significant advancements in autonomous mobile robots and navigation of a factory floor using an array of sensors to capture, process, and make logical decisions based on the sensor data and programming of the robot.
Yeah, Ryan, also, with all the new robotic technologies that are being developed, there are some core enabling technologies that are helping advance robotic applications inside and outside of manufacturing. A few of these are 3D simulation and digital twin technologies that are changing the way we view and that we process data. And this is leading to developments in robotic applications such as predictive maintenance, visual programming, and other advancements, including the use of augmented reality to display screens to operators and engineers in a very intuitive way. So when you combine some of these technologies with other technologies, you begin to have a very powerful set of tools enabling the growth in robotics that is required in order to bring robots to the masses into these new markets. These enabling technologies are critical in allowing robots to become easy enough for anyone to interact with, program, and use them, which will enable the adoption of robotics within manufacturing to accelerate over the next 5 to 10 years. Ultimately, these technologies will become the backbone of how robots will be operated, programmed, and used for the next 1 to 2 decades.
Thanks, Evan. I'm going to talk about some of these enabling robotic technologies in a little bit more detail. So 3D simulation is an important technology. It's been prevalent, but it is becoming more prevalent, allowing us to design and build in a virtual environment. Using physics models, we can establish a model of a system that's almost identical to the real world. What this allows us to do is quite a bit of testing and fast failure that would cost a lot of money and time in the physical world. Using simulation, we can test, fail, rebuild with improvements, and retest all within a few hours or days, when this same testing would most of the time require physical builds, modifications to these builds, and these types of testing and builds can take weeks and months in some cases. Digital twin is a newer term, and it's essentially very similar to 3D simulation in that we take a 3D model, we match it as best we can to a physical device, machine, or a system. But the main point and biggest difference of simulation and digital twin is that digital twin allows us to communicate how the physical device, machine, or system is operating, and to be able to display real data of that operation real time on a visual representation of the model of this device, machine, or system. So imagine being able to look at a picture of a machine or a 3D representation of a machine on the screen, being able to click on it and being able to access a cross section or one of the components of that machine, and then being able to see in real time a device inside of the machine like a heat sink or a computer chip or some moving component, and you can actually see the temperature of this component overlaid on top of the digital model of the real machine as it's operating in real time.
So other really incredible enabling technologies that we're seeing are machine learning and augmented reality. Machine learning is a very interesting advancement in programming methods, and it is really aimed at bringing advanced applications closer to reality for a lot of users. In order to advance the ease of use of robotic applications for manufacturing, we really do need this technology going forward. Let's take a scenario that is very prevalent in manufacturing today. A company wants to use a robot to pick up parts and put them into a box. One of the challenges here is that most companies don't make one single part. Rather, they make a lot of different parts, and each one of these parts needs to be programmed into a machine vision system so that the parts can be identified properly, and the picking location of these parts needs to be passed on to the robot. Until recently, this type of application would have required hours and hours of engineering effort, and most likely resulted in smaller companies being prohibited from these applications, mainly due to cost and complexity. Using machine learning, we can simply tell the camera system what it's seeing, and after a few classifications, it starts to learn the attributes that represent that specific part. Machine learning is a technology that is growing and growing as computational methods become faster and faster, and we're able to process more and more data. And it is really just on the edge of becoming a manufacturing standard. Exciting. You also have augmented reality, which is another technology that is being used to advance the use of robotics and large data sets. This technology involves the use of the physical and digital world overlaid on top of each other. Imagine putting on a pair of glasses and then being able to look at a part on a table in front of you. Now, imagine being able to see the assembly instructions overlaid onto the part, and even arrows that can point to an area of the part indicating where you need to start. This technology is rapidly becoming a replacement for user manuals, work instructions, and other form of operator guidance. We are even seeing this on the latest military aircraft, using the cameras mounted outside an airplane to allow you to see the airplane as if you were sitting in a glass ball in the air. No more blind spots because of an obstructed view. This technology, again, is dramatically increasing as the ease of use and the methods of implementing it are becoming more viable for the different technologies, what with tablets, as we mentioned, with glasses, and it is really becoming a technology that will really redefine how operators interface, and technicians, maintenance people, with robotics and just technology in general.
So to close out this section of the learning objective, we're going to talk about a few more enabling technologies, those being cloud architecture, feedback and haptic sensors, and remote teaching and guidance. These three enabling technologies, they don't have a significant impact today on robotic applications, but they're enabling some really impressive applications to be developed and deployed rapidly, while also allowing the operators the ability to teach and move robots from remote places while using the data from sensors on the robot in almost real time. So rather than talk about each one of them individually, I'm going to talk about an example of these technologies used in manufacturing today. So a great example of all of these technologies combined into one application is the military drone. This is a technology that Evan referenced in the past about using augmented reality, but if you think about how augmented reality comes about, these technologies enable that, and this is a technology that the military drone is a technology that would not be possible without the data from the sensors, remote piloting ability using the cloud, and the feedback systems that allow a remote pilot to operate an airplane as if they're in the cockpit. This example combines almost every single enabling technology that we've talked about, and the advancements that we're seeing from this will allow us to do things such as remote operation of, let's say, a casting furnace or a press, or if you think about machine vision and having to make a decision, if the computer can't make a decision, somebody could actually see what the camera is seeing and make a quick decision for them. That would also then enable the machine to learn what the operator remotely just classified into that machine vision system. So it's pretty amazing to see the enabling technologies and what they're doing to help with robotics applications. For the next learning objective, we're going to talk about avoiding the gee whiz effect when deciding if new robotic capabilities are right for your application. I'm going to start off this learning objective talking about when you shouldn't use a robot from a business perspective. There's a lot of reasons why we should use robotics, but before we get to that, Evan and I are both going to talk about some of the reasons why you shouldn't use a robot. This list is not meant to be exhaustive, but there are definitely some good points to review when asking yourself if a robot makes for a good investment. You should always be asking yourself about the why when thinking about making any process change, regardless of robotics or not. This is even more important, though, when you're considering a step function change, like using a robot in place of a manual task. From a business perspective, you should be thinking about the investment, its impact on your process from a financial standpoint, and whether it makes sense to automate. You also need to be thinking about the other opportunities within your process and whether solving this problem is the right problem to solve, or is there a better problem-solution combination that can get you a win. Finally, you need to be thinking about the business objectives for this specific process or product line and ensure that you're aligning your automation goals with the overall goals of your company. We'll talk about that in more detail in a moment.
And from a technical perspective, we're going to be diving into some of the biggest pitfalls that really why you shouldn't use a robot, in that sometimes there's just a simpler solution or something off the shelf, like an OEM piece of equipment that exists. And sometimes from a technical perspective, robots may be thought to be the solution for something that really just needs a standard work procedure and or just a verified process. Another reason from a technical perspective that robots really shouldn't be introduced is for the sake of change or advancement, just so that a new technology can be introduced without a real end goal for why the robot is being introduced. And finally, as technology grows, the complexity that robots can accomplish is growing as well. But sometimes the complexity of a task is just too great for the investment, and sometimes it's just not worth having a robot if their repetition is not there. So I'm going to let Ryan jump into the business perspectives to begin with.
Thanks, Evan. So the first thing that I want to talk about, the first thing I think you should be thinking about each and every time you decide to make an investment in your business, no matter what, is ask yourself the question, is this a good investment? Am I spending the money we have on the right things? When it comes to using a robot, a few major points to think about. What is the labor cost associated with a given task? You have to think about this from the perspective of the labor cost, and then also where we are economically. We have to think about labor being available, so that is something else that drives cost up. If labor is high in a given area, you also need to be thinking about what machines are part of the upstream and downstream process and how are they being utilized today. So, machine utilization is critical, and putting in a robot doesn't necessarily affect the overall process if you have too high of utilization of machines. We'll get into that in a minute. Does using a robot in this process change the quality metrics of this process? And another question to think about is there a bigger bottleneck in the process that we should focus on immediately? So a couple good examples. A good example for low labor costs would be a production process that can be completed in one shift and doesn't require multiple shift or overtime work to complete. In this case, the cost for the robotic cell might only pay themselves back over multiple years, and the cost may outweigh the investment benefit. Putting together a good ROI analysis using that scenario is helpful. A good example of machine utilization being too high already. So let's say you have a machining operation, and the goal is to increase throughput for that process. Somebody suggests installing a robot into that so that you can eliminate the cost of the operator having to load and unload the machine. Sometimes, if the cycle time of the machining process is longer than the changeover time of the part change, it does not make sense to install a robot, because the robot would essentially replace the operator, but there would be no throughput or top-line increase. There's just a lower cost associated with that operation, most likely not making such a difference to justify the cost of the robot cell. In the scenario where there's a high scrap rate and the robot is installed to perform a task, this robot may not change the scrap rate, and if that is the case, this would be a poor investment. So thinking about how an operator is affecting the scrap rate before you apply a robot to solve a problem that isn't actually being solved due to scrap rate not changing, this could be a poor investment. This can be seen in projects where a pick-and-place robot's installed, but the robot is moving scrap parts from one process to the next. This didn't actually change anything in the process overall, even though it did remove a bit of labor from the process. Robots can also have a big impact on a process bottleneck, so you really need to ensure that the process you're changing is the right one. If you don't ensure that, and you have a different bottleneck downstream, you may just be simply moving the bottleneck in the process to a different area, not necessarily changing the overall throughput. For that matter, you may not be changing the scrap rate or the other metrics required to consider the project a success. In the event of ROI, all of the items listed here do need to be reviewed collectively, and not one of these is listed as a single thing that should drive a robotic installation or not. All of these collectively will drive sound investments into the right robotic system for your process. So let's talk about solving the wrong problem. Some of these bullet points I'll talk about, using a robot that could be considered the wrong reason. So another case that could be considered the wrong reason to use a robot would be to implement a robot when really an operator just needs better training, better standard work to follow, or even putting in a robot for the sake of change or because it's a cool thing to do. In a lot of cases, using the previous slide bullets, you should have a good idea of what the robot's going to do and how it's going to impact the process and associated costs of the process or throughput that will be gained in the associated revenue increase. When you're evaluating a robot for use, you must make sure that there is not a very simple solution to be implemented. Let's think about the scrap rate of a process and the previous example saying that a robot makes a good investment if the scrap rate is reduced. Let's assume this robot's performing a task, and this task becomes repeatable because the robot is performing it. What if there was a simple way to guide the operator to perform the same task, such as a template placed on a part before a hole is drilled, or a visual aid to be aligned with the part in order to make sure the proper cap is always placed on the part at the correct location? These small training guides or standard work procedure improvements can cost very little to implement and can lead to very real gains. Ultimately, what I'm trying to say is don't just implement a robot because it's a way to drive change or it's the cool thing to do or because it's seen as an advancement. Be practical in the robot use case and its associated improvements. The last thing I want to talk about is, from a business perspective, when you shouldn't use a robot is when it's not in line with the business objectives or strategy. I started this slide off scenario being somebody wants to install a robot at the end of a production line. And you have to think about that production line and the business objective. So if the business objective is growth, or maybe it's to maintain your planned production, or in some cases maybe it's to exit that product line. Every business has a strategy, and in some cases it can be to grow either a specific product line, maintain a certain market share, or exit this market. All of these business cases will have an impact on the return on investment associated with this particular project. In this scenario, we can assume that you're thinking about installing a robotic cell and ensuring that it not only has a return on investment initially, but also thinking about the business objectives over the life of the robotic cell will be important to show the value to the executive management team. Most companies have some form of business objective setting specific to product lines or part families, and the executive staff that's approving these capital expenditures has a really good understanding of the long-term perspective of the company, you should really make sure that you're aligning your ask for capital with the business objective. Great example of taking on the wrong solution or trying to solve a problem that doesn't need to be solved is installing a robot on a line that the line may be, that product may be phasing out in 2 years. So while you can amortize the cost of a robotic cell over 7 years in some cases, you may not want to do that if the product line is going to be obsolete in 2 years. So just understanding your business objective and specific product line objectives is really helpful from a business perspective.
Thanks, Ryan. Business drivers seriously can be a massive indicator for when to use robots, but technical fit is necessary to understand. As discussed previously, there are 4 big obstacles to kind of consider when researching robotics, and this is by no means is an exhaustive list. This is just kind of what we've seen in the industry is sometimes just a simpler off-the-shelf solution. And again, we're going to harp on this a fair amount, but robots are not needed from a business and technical perspective to replace an unverified or faulty standard work procedure. Also, the necessity for change, advancement is not a good driver, both, again, from a business perspective and a technical perspective. And finally, complexity and repetition of the process. So the first idea we're going to dive into is there a simpler off-the-shelf solution? So before investigating robotics for a certain application, it is well worthwhile to research the process to be automated for any OEM solutions that are readily available. A good example for this is if you have a specific product that needs to be marked with a specific manner of maybe a barcode, letters, or what have you. A good idea, maybe you think a good idea is to take a robot and etch those on. But simple label maker, something, a simple etching machine might do the exact same task for much lower risk and much lower cost. So just doing a simple research into if there's an OEM solution readily available, it may reduce a lot of headache down the road. And again, a tried and true product designed specifically for a certain problem will typically reduce risk for project success. It is also important to consider the complexity of the process to be automated. Sometimes a simple linear axis system for picking and placing material can be much less costly and complicated than a multi-axis robotic system that achieves the same purpose. If you're trying to pick up a part from one conveyor and bring it to another, it might be the job of a simple pneumatic gripper to pick up and place that part rather than a 4, 5, 6 axis robot to accomplish the same task. And finally, robots can be exciting for their ability to flip, turn, and manipulate material in all sorts of ways. However, it is important to understand the assembly and manipulation processes. Are they actually necessary for application? Sometimes material handling, for the sake of material handling, will not result in proper ROI from a technical and business perspective. The second idea to consider is the process to be automated, and because robots are most well suited to address verified processes that have a set of governing standard work procedures. As Ryan mentioned, from a business perspective, it might be applicable to just add a simple template for an operator to do an assembly process. And as we're going to go into, sometimes robots aren't necessarily the fix to a certain process, such as if you're going to add a robotic measuring cell to pick up a part, measure it between a micron, and align it to 1/10 of a millimeter, when a simple fixture, a mechanical fixture, and set of instructions would suffice to do the same type of alignment. Another example would be a robotic grinding cell. If you have parts that are coming out consistently out of spec and need to be grinded, instead of implementing a robotic grinding cell to fix those defects and allow product to go down the line in spec, it probably is worthwhile to address the root cause of the imperfections and the core process that might be missed by implementing a robotic work cell into that. And finally, if a process is lacking and results in bad and or deviated products, robotics will typically amplify this problem rather than solve it. If you're seeing a certain process result in bad products, and you're going to think, and implementing a robot is probably not going to help that. The blessing and the curse of robotics is that they will do the same thing every time, all day. And if a process yields substandard outputs, so too might the new robotic solution. Another aspect to consider from a technical perspective for when to use robots, as mentioned from a business perspective, is change for the sake of change, or change for the sake of advancement. Adding a robot because of the technological advances it will give your company rather than the benefits it will yield typically will end in an end result that may be murky at best. You will see the results of the robot and not understand, is it actually accomplishing its job? Again, talking about the end result, change for the sake of change may result in an undefined end result that may not meet the ROI standards or what is expected from the robots. Finally, this is a key to robotics, is not to use the word always loosely, but starting with a problem and working your way to the correct technology to fit the problem will almost always be the #1 driver for a successful project. If you start with a robot and try to find a problem that robot will fix, the end result, again, may be murky at best. So the last item to kind of address is the complexity of robotics. So if an OEM solution does not exist for the process to be automated, and there's a driver for the technological upgrades beyond change, and there is good standard processes in place, the last point to consider is complexity. Robotics can do some amazing tasks, as noted earlier. However, with what robots can do, they can run over boulders like terrain, they can fold laundry, they can navigate rush hour. Robotics are incredible technology advancing. However, there are some basic points to consider when selecting a robot, especially in industrial robotics. First is, robots typically struggle to complete high dexterity material handling. This isn't to say that a robot cannot achieve a certain highly dexterous task, for example, tying a knot. It is to say that the cost associated with high dexterity tasks is much greater than a simple pick-place machine that has a high repetition. The point of this is simply to note, to keep in mind when assessing a prospective automation project, what is the dexterity required for that maybe an assembly process. Second, robots thrive in environments where the inputs into their work area are properly characterized. This means that high variation product that has low volume, think production runs of 5 to 10 parts at a time with thousands of variations during the day. This can increase the risk and cost of an automation solution with robotics. In order to deal with variation, robotics typically require machine vision, tool changeovers, and complicated tooling. If the volume each variant does not justify the tooling required, robotics might not be the right direction. Third is part repeatability. If a product is not able to be provided to a robot in a known fashion, the cost and risk of the automated solution increases dramatically. Items to note on this point are product tolerances. How big can the product be? How small can the product be? Product appearance. Will the product have varying colors, features, etc.? And product conveyance. Will the product be shown to the robot right side up, at an angle, upside down? Each variation or repeatability can cause a spike in complexity and may be worthwhile addressing before going down the robotic path. Fourth and final is variation in process. You may have a high volume, low variation product that is consistently and repeatably displayed to a robot, But the last point to consider is what happens when the robot sees the part. If the process is to automate is multifaceted, then as a result, the complexity of the work cell design may spike. As mentioned previously, robots are very good at doing the same thing every time, all day. If a robot is asked to do a large number of tasks, a minimal number of times a day, this may not be the best application for a robot. This may seem like, what we've outlined, these business and technical perspectives, a list to dissuade from robots, but the reasons to use robots covers just about all other situations and discussed above, and this is what makes robots so exciting and adaptable.
Great. Thanks, Evan and Ryan, for your instructions so far. Let's pause here to check in with the webcast viewers for a 45-second poll. At this point, I'd like viewers to confidentially share your primary reasons for your next robot purchase. So let me go into the poll question here and send you the survey. So look at the survey results. We're asking if the reasons are to increase throughput, increase quality, eliminate one or more bottlenecks, do dangerous, dull, or dirty things that we can't hire enough workers to do, save jobs by increasing competitiveness, eliminate jobs and use displaced workers in other areas, or some other reason. So check all that apply on the survey, and we'll give the poll results and see how you did compared to the respondents in our robotic research report after this presentation and before the Q&A session at the end. So just a reminder, after you take the poll, and any time during the presentation, you may ask questions of the presenters using the Ask a Question box in the interface. Okay, now we'll go on to the remainder of the presentation. Thank you.
Thanks, Mark. We're going to get into the last topic of the learning objectives, which is to receive some tips and tricks about robotic and robot system applications. I'm going to let Evan kick this off, and then we're going to take turns talking about some of the bullet points here.
Thanks, Ryan. The first and biggest point with robotics is they're all about the reduction of risk and complexity. And you really want to start from this vantage point. We're going to dive into a few mitigation techniques to consider from the onset of an automation project. The first being definition of scope. A clear definition of all sub-processes will yield clear directives and objectives along with a path forward with the correct technology. Some tasks to understand are: what are the sub-processes? What are the tolerances? What are the inputs into the robotic system? What are the outputs from the robotic system? With a clear scope, it is easy to see a conglomeration of the latest and greatest technologies as the solution. However, as mentioned previously, it is important to follow the old adage, the simpler, the better. So with that being said, it is sticking to proven methods where possible for automating tasks can prove the difference between a wildly successful one and one that goes off the rails. It's better to not reinvent the wheel and use what is available, especially from a robotics standpoint. As we're seeing the industry grow and increase, there are becoming more and more off-the-shelf tools that become available for end users to really allow them to have better, quicker startups and quicker integrations. And finally, it's important to have a general understanding of the safety standards that are expected to be met for the robotic work cell. The level and method of important safety features will drive hardware selection and process implementation. It is highly important to not let this get lost in the excitement of implementing a new technology.
So just kind of summarizing a few of the things we've talked about already and adding some more, we think it's really important that you understand your company's goals and return on investment that are critical in establishing. You got to establish a budget for your project and the payback. Without this, you're going to have a very tough time getting capital for your project and being successful. Some of the points in defining these things, you should know your audience. So if your main drivers are safety, ensure that you include someone from your environmental health and safety group in your project. If your main driver is throughput, you should definitely include an operations person in your project. Always make sure that you have your maintenance and facility staff involved in your projects as well. This will lead to much more clearly defined projects and success of the project. Make sure that you define your vision for the future, the long-term impact that it's going to have on the company or corporation. Remember that vision allows everyone to understand how this system will benefit them, their performance metrics, and why it makes sense. Without a clear vision, you can't be successful implementing a robotic strategy. Include your team so that you have clearly defined deliverables. This will ensure that when the project's coming to a close, you can measure your success and everyone will agree because they helped to define those deliverables. Nothing worse than getting to the end of a project and thinking you're successful for someone else to say, but what about this thing? Make sure that the system performance metrics tie back to your company performance metrics. For example, if you measure throughput in parts per hour on your machine and you're building a welding cell, so if your company measures throughput in parts per hour, you're building a welding cell, a robotic welding cell, for example, don't measure your system throughput in linear inches of weld or runtime because it won't be translated back to your company's metrics, which are what drives your overall success.
Perfect. And finally, we're going to just go through a few good questions to ask yourself when you're first looking into robotics. Because a big reason for robotics and the big driver for the system is they really depend on the interaction with the installation environment. So a few good questions to ask is, will the robot work in collaboration with humans? Will it be automatically or manually fed? Will there be inspection or verification of outputs necessary? And how will the robot handle variation in products and processes? The answers to these questions drive a large majority of the system, such as, will you need machine vision? Will you need a collaborative robot? What safety precautions will be necessary? It will drive how big of a robot will you need? What kind of robot will you need? How will you interface with the robot? Will the robot have to talk to a cloud? Will it talk to a PLC? Will it need to be on an SQL server? And then what will be its interactions with other technologies? Are you going to need 3D vision? Are you going to need 2D vision? What kind of motion control do you need? So these are really big questions to ask at the beginning because these will drive a large majority of the system development and the project scope going forward.
Great. Thanks, Evan and Ryan. On that robotic research I mentioned earlier, we had an open-ended question where survey respondents could provide advice. These responses cover robot specification, installation, and integration, as shown here on the slide. So it's kind of fun to see people responding to the survey and giving their advice, especially after all the good advice you gave. I won't go over these bullet points. They'll be there in the survey. But I would like to get to the poll response. So everybody had an opportunity to take the survey, and now we'll look at the survey response. So I'm going to send the results to you so that you can see how we did. So it looks like increased throughput and quality and doing dull, dirty, and dangerous things were the highest responses. I would call those probably all within the margin of error, those top three applications. To compare, in the November 2019 robotic research report, we broke out this question in even more detail with 13 possible answers. And the top 7 results were 64% increased throughput, 52% increased quality, and the next 5 were a statistical tie around 27 to 30%. And those were eliminate bottlenecks, do dangerous things, do things that we can't hire people to do, save jobs by increasing competitiveness, and do dull things that workers usually don't want to do. Great, and so now we do have a few minutes to go to the Q&A session. Let's just review how that's going to work. The audience listening live can type questions for today's presenter in the Ask a Question box on the screen, and we'll answer as many questions as we can. Within a few days, the presentation will be available for on-demand viewing along with a link to the quiz for potential PDH credit. We'll post the archive on the Control Engineering website, and we'll send you an email message with a link connecting to it directly and to related resources after it's ready. And now on to the questions. How can PLCs be used and integrated with robotics applications?
That's a great question, Mark. And PLCs can offer a lot of different benefits to robotics. I've seen PLCs used with custom instructions to actually control robotics from actually controlling the joint and linear moves. PLCs are great for storing data and calculating, offsets that allow robots to do a high variability of assembly processes and material handling processes. They're really also great for just controlling the robot's overall state and ensuring that you have a really strong control system that is low failure rates. PLCs are just a fantastic way for allowing robots to interface with a larger environment and have access to the cloud, SQL servers, all of that good stuff.
Good. Here's a question. We have a machine with a PLC run as an app on an IPC, and the PLC has drivers controlling 4 robots directly. Is that kind of thing something that you see often? Is that the way of the future, do you think?
I can take that one. So the machine, let's see, we have a machine with a PLC run as an app on an IPC. PLC has drivers that are controlling 4 robots directly. So I would say, definitely PLCs and IPCs being mixed in a work cell is where I've seen a lot of applications going. I've even seen PLCs being eliminated in favor of IPCs. It really depends on the response time and the robustness of the application you're looking for. What kind of hardening you're looking for from a manufacturing standpoint. But I do see PLCs being virtualized on IPCs more often. Great, thanks.
We talked about safety. We didn't talk about cybersecurity, though. Could you maybe address some IoT cybersecurity issues as it relates to robotics?
So I'll take that, Evan, and then if you want to add to it, you can. I think there's a lot of risk depending on what manufacturing sector you're in. Take aerospace, for example. There's not a lot of accessibility to the outside world, when you're talking about network infrastructure. The ability for robots to be on a network internal to a facility, I think, is happening. Seeing a lot of applications where data can be fed up to level 2 systems and back into operating rooms, operator stations, etc. within a facility. Accessing facilities from the outside, I see there's still a lot of risk there that's being mitigated through new hardware and new software technologies. There's a lot of risk being mitigated through cloud technology. There's like there's many companies that are diving into doing applications in the cloud that can be accessed, so everyone's just talking outbound to this cloud application, which eliminates any inbound connections. And so there's a lot of things being done to mitigate that risk, but I still think cybersecurity is a risk that's being addressed.
Great, thanks. Evan, anything to add? Are you good?
No, that's a really good way of putting it, Ryan. I don't have really anything else to add on that.
Good. Here's kind of a out there question. How far off script can the robots go?
So this is a pretty cool question, because the answer is really how far can technology go? As we were talking earlier with deep learning, machine learning, machine vision, it really depends on what kind of technology you have interfaced with the robot. We have seen some incredible systems that use deep learning to allow robots to adapt to brand new products that they have never seen before on the fly, simply because it knows how that part is classified and how to manipulate that classification of a part. Your typical robot with no external vision or external sensory input is really going to just do what it's told to do. But you can use 3D vision, 2D vision, a lot of external sensors to allow robots to do some pretty incredible tasks through the use of computational methods.
Great, thanks. You addressed safety a little bit. Any more advice about safety? How do you manage safety with robotics?
Safety is really a key thing to understand, and there are some levels. The first is if you're trying to implement a robot with humans and you want a truly collaborative robot, there are truly collaborative robots that will be able to work in tandem with humans. Then you can create collaborative environments where you'll use an industrial robot that is not padded, it doesn't have sensory feedback, but that robot can be allowed to go into safe move and actually turn off via the use of laser scanners and different safety-rated devices to tell the robot when a person or when a foreign object is close to it. And the last and probably most common way of creating safety around robots that is seen, at least from a physical perspective, is actually interlocked guarding around the robot that protects peoples and operators and maintenance from actually getting inside the work cell while the robots are moving, using safety-rated locks to allow the system to know when people are and when people are not in the work cell.
Great, thanks. That was a 2-for-1. Evan also answered the next question. So how about electrical safety for robots? Is there anything special when considering how the robot is connected electrically to the rest of the systems? And this might be our last question.
And can I just give just one thing I want to let the audience know is the things that Evan described about safety and robotics. There are some really good standards out there that you can find, ANSI and RIA and some other standards boards that have published, and OSHA has adopted those standards in the U.S. and there's other SIL level standards for Europe, but that you can actually read and get a really solid understanding of how to protect a robot in an application.
Good. Well, let's link to some of those articles that we've done on that point, and then we'll link to some electrical safety resources as well. And now we'll close today, and thank you for your strong support and your knowledge. Thanks everybody for the great questions. We'll try to get to as many of the unanswered questions offline as we can. Thank you to our presenters, Evan Gonnerman and Ryan Wasman with Concept Systems for sharing their time and expertise. And thanks to our sponsor, Denso Robotics. So now that we're just about finished, we'd like to hear how we did. A short survey will pop up on your screen just as soon as the webcast event ends. Take a moment to complete it. We use this information to improve our webcast. Finally, on behalf of Control Engineering and CFE Media and Technology, thanks for attending. Now concludes our webcast. Thank you and goodbye.